Okay. So, how's everybody's Friday so far? You do remember you have homework due on Monday? Okay. How's that going? Are we beyond problem 2? Then we're on a good track to finish it all by Monday. Let me know how it goes. It is a little bit longer, so let me know how it goes. But just let me get. I have found my pen. It was, of course, under the couch, even though I never used it in the house, but my money is on a certain toddler in my house. Found the pen and took it out. All right, so let's get busy generalizing our viscosity model. So in this, today, we're gonna generalize this model for Newtonian viscosity. And always when defining things, it's always useful to have that parallel plate model in mind. So to remind you, we have a bottom plate that is moving at a constant velocity dx, though I refer to a general coordinate velocity vx as well. So basically, there's Vx, this is the maximum velocity on the bottom plate, and the top one is kept stationary, so that's where my Vx and all other velocities are 0. Okay? My Vy, I'm assuming there's nothing going across, so there's nothing driving the fluid in general going across. So Vy is 0, so I have only one coordinate velocity. And basically, in order to maintain that state, I have to exert constant force on this bottom plate. When we divide force by the area of the plate, this is what we refer to as stress, and in this case, it's a shear stress. And basically, to maintain the situation, I have to constantly provide that force, right? So now, that is the sort of the force view. So now I have all these layers moving at different velocities. And I can basically see that even if I immerse myself inside the fluid, and I put sort of like an imaginary plate inside the fluid, okay, parallel to both the others, then below that plate, I'm going to have layers of fluid with larger velocity. And above that plate, I'm going to have layers of fluid with lower velocity. So I can imagine that basically that plane feels the shear stresses as well, shearing stresses from the fluid itself. And that's what I refer to as a shear stress in the fluid. In order to have it, or viscous stresses in the fluid, in order to have these viscous stresses, I have to have layers of fluid at different velocity. They don't have to be layers per se. Here they're layers because I'm parallel to the plates they're moving. But overall, I have to have differences in velocity to feel those stresses. Okay? So those are the viscous stresses. And they're dynamic stresses in the sense that they show up because the fluid is moving. Otherwise, you would not have it. There are stresses that are there even if the fluid is static, right? That's the hydrostatic pressure. And I kind of feel them all around. So they're always normal to the surface that they're acting on. But these can be shear as well, or can, in general, have a very general direction. And we, in terms of formulas, so basically for a Newtonian fluid, I'm saying that the shear stress, which is force per area, is equal to the negative viscosity that for Newtonian fluid doesn't change, it's constant factor mu, dvx dy. I also refer to this minus dvx dy as, what is that? Shear strain rate or shear rate. So you will often hear shear rate or strain rate. It's really shear strain rate, but it's a long thing to say. Gamma dot, right? So my general model here is tau ix is equal to mu gamma dot, okay? And in a non-Newtonian fluid, it's the definition of mu that changes, and then we refer to it as eta. So it's just now generalized viscosity that could depend on gamma dot as well. In a Newtonian fluid, mu is just mu, it doesn't depend on gamma dot. Or rather, it's a very simplified function of gamma dot, which is a constant. So I don't depend on shear rate. In Newtonian fluids, in non-Newtonian, I do. So generally speaking, what I'm going to talk about, I'm going to talk about it in the framework of Newtonian fluid. However, it is really applicable for any other fluid. It's just that my relationship between this mu becomes more complex. That's all. Okay. All right. So I said, okay, great. This is a simplified situation where I had one velocity that was non-zero. All the others were zero. What happens when I actually have velocities, general velocity, right? And let me actually, I'm going to go and I'm going to switch to writing. Oops, that's not what I meant to do. Okay, so basically my tau yx is equal to minus mu dx dy when Vx is Vx of y, some non-zero function, and Vy is equal to 0. And that was my whoop, that's not what I meant to do. Oh well. And my Vy is 0 and Vz is 0. Okay. And the shear stress was in a parallel plate situation, okay, where I had these different velocities, right? So I could strike any plane. Let me try to find where am I? No. Where are my colors? Arrow, no. Ah, there we go. So if I strike a plane, okay, I'm feeling a shear stress tau yx, and that's the same direction of the force acting in this system as well. Shear force. So basically, this is my tau yx. It's shear stress in x direction. Okay. So that's the x part. Acting on a y plane. Yes? This plane is a y plane. I will refer to coordinate vectors as delta y. So this is essentially, I could look at it as delta y and delta x. Because that's what BSL uses for coordinate vectors. I like EX, EY, EZ. BSL doesn't agree. Or IJK. Oh well. Going with the flow. Yes.
So when there's like individual particles in like that one plane, they have shear force, right? Are they accelerating or are they at a constant velocity?
Could be either. So within the layer, okay? So in this case, acceleration is acceleration in time. Okay? This is actually assuming steady state. So each Vx of y is not Vx of y. They're not necessarily accelerating. It's just that neighbors have different velocities. So there's a spatial gradient of velocity. Okay? It's an excellent question. They don't necessarily have to accelerate. Nobody's accelerating here. So there's temporal derivative and there's spatial derivative. Mathematically, they're defined, math couldn't care less. So you have a variable x and you can take a derivative with respect to x. Or you have a variable y, t, you can take a derivative with respect to t, right? But in physics, we care. Right? So in that sense, here, there's no temporal change here. This is steady state. Steady state. No dependence on time. Okay? All right. So generally speaking, all of my layers or fluid components or fluid, however I like to look at them as a sort of fluid packets, they have x momentum here. And that x momentum is transferring upwards in y direction. Okay? So that's another non-force view. It's momentum view, if you say. So particles, okay, we have x momentum. And in fluid, I refer to x momentum density, really, rho Vx, right? Transferring in y direction. So this shear stress is also momentum transfer, x momentum transfer in y direction. So now that we've mastered things in this, essentially it's two-dimensional view, but only with one velocity being non-zero, we want to move to a general case. So I can actually generalize this in the case that I actually have velocity vector, which is a function of x, y, z. And that velocity vector has Vx, x, y, z component, Vy. I'm still in a steady state. I could depend on time too, but I'm not gonna gain anything. There's some shortcuts that I'm apparently pressing here that I don't know about, that jump 2 slides. Vz of x, y, z. Okay. So now I have 3 different velocities in most general case. I'm not just like moving in this simple mode. It could be whatever movement. Right? And now I'm going to describe how this momentum transfers, or what are the forces acting on a fluid. I still need to separate myself and look at it across 3 different planes. And if I sum up what happens across 3 different planes, I'm going to describe what's happening in 3 dimensions altogether. So I'm going to still have tau yx. And tau yx is going to tell me about the x momentum transfer across y plane. But I will have also x momentum transfer across x plane and z plane as well. Okay. Likewise, I'm going to have y momentum transfer, and that can go across x, y, z plane. And finally, Z momentum transfer, and that can go across X, Y, Z. And so I need basically 3 by 3 numbers to describe what's happening. And that's essentially the generalization. So first I'm gonna, since we started at tau y and across y plane, I can across that same plane in a general fluid. So if I have now X, Y, Z situation, so if this is, most often I say this is X, Y, Z, so I'm gonna keep that. So where is my y plane in this coordinate system? It's all of these. So some general y plane, whoops, is here. Right? Because it's orthogonal to, this is my delta y, coordinate vector in y direction. So this is now y plane. And my general velocity vector, okay, one of these days I'm gonna stop. My general velocity vector is something like, I don't know, something like this. Okay, so I have all of the V, just V. So I have my rho Vx, rho Vy, and rho Vz to transfer across this plane. Okay, so basically what I'm gonna use is tau y, which has tau yx, tau y, and tau yz to describe all coordinate momentum transfers across y plane. So this describes rho Vx, rho Vy, and rho Vz transfer across y plane. X momentum transfer across y plane, y momentum transfer across y plane. So that goes that's normal stress. Right? Z momentum transfer. So in that case, shear stresses are tau yx and tau yz, and tau yy is a normal stress. Okay? Because it's the y momentum across y plane. So that's acting normal. Yes? So what is the direction of tau yx? In terms of x, y, z? What is the direction of tau yx? X. Just like here, in this case. This was x direction, right? Just in 2D. So in 3D, that's going to be the case with just x on this plane, right? So we're going to have, this is tau yx. And technically, it's considered positive if I have the sort of what we call fluid and lesser y is now here. Yes? Those are my lower y coordinates. And on the other side are the higher y coordinates. So it's positive if this fluid is acting on some, let's say that the fluid is here and there's a solid here, an imaginary solid, if you will. Okay? And the action of the fluid is on this side, then that tau yx is positive like this. Okay? That's a convention. And then what is the direction of tau yz? up, which is z direction. What is the direction of tau y? Or you can okay. So again, this is a convention and it could be flipped. So we are using convention that this is x momentum transferred across y plane, and that's why I have the direction of x. Okay? Is the action of the x momentum. Y momentum across y plane and z momentum across z plane, y plane. Yes. And this in self, so this is a normal stress on the plane. Normal stress on y plane. And these two are shear stresses. So I need a vector to describe how all of the momentum components, rho vx, rho vy, rho vz, are transferring across y plane. Okay? So note that rho v is my momentum. It's a vector, right? Everybody done taking notes? Questions? There's palpable silence in class. So what is troubling here? One thing is remembering what is first, what is second, like in this tau yx business, right? And what helps me, and it could be the other way around, it's a matter of convention, so yes. And what's gonna flip you a lot is that solid mechanics uses different convention. Unfortunate, but the reason why we are using this definition and this also, so in solid mechanics, you're going to count stresses that are extending something as positive. In this convention, those are negative as compression. That is. So this is kind of positive, right? It just kind of like compressing this box. Yes? So the convention is opposite, and which way you decide to call something plus or minus is really arbitrary. Different communities in solid and fluid mechanics did so differently. But ultimately, as long as you stick to one convention, you should be okay. Questions? Should I repeat this? Or do it in a 2D example, maybe? Let me do something like this. So basically, if I had 2D, I have a box in coordinate system. So what are the possible, we can look at it this way. On this is my y plane now, right? So those are two y planes. They're orthogonal. So sort of lower, and for some reason, and upper. So what shear stress am I feeling on the lower y plane? Tau yx. So that is my x momentum transferring across y plane. In a general case of having a velocity vx, vy, okay, in 2D, what other momentum is transferring across y plane? Coordinate momentum. I mean, my momentum is rho v. And really, when we are talking about fluids, we are talking about momentum density. Because I don't have a solid object of mass m, I have fluid of density rho. So I have just successfully now transferred some rho vx across that plane. What else do I need to transfer? Rho vy. Yes? So what describes rho vy transfer across y plane? How I'm going to call that? Tau yy. So if I place an imaginary plate anywhere in the fluid, that plate will feel shear stress here, tau yx, and a normal stress tau yy because of the differences in velocity of the fluid. Yes? And yes, if I place, that doesn't have to be imaginary, if I place an object, right? And that object has one side that is flat like this, those are the shear stresses I'm going to feel. Yes? Same thing on the upper side. So here, it's just that one of my sign convention is going to flip. Just if I actually imagine that this here that I drew this rectangle, if it's actually a solid rectangle, then fluid would be around it, right? So I would feel those stresses from the top side. And sign convention changes now, so my tau yx nominally points in an opposite direction, because from the coordinate standpoint, here the fluid was below the object and had lower y coordinates, the fluid did, right? And up there, the fluid has larger y coordinates than the object itself, yes? And the way we think about that is like we normally, like if this was really an object, there would be a normal pointing in this direction here to the surface, and up there the normal is pointing in the opposite direction. So shear stress has to change sign as well. Okay, what do I have on this side here? So this is my x plane. Let me change colors here. I'm going to go to some green here now. So this is my x plane. And this one is upper. Upper means that it's in this coordinate system, it's in the larger x's than the other one. Okay? So this lower upper refers to coordinates in this particular coordinate system that I drew here on the side. And you always have to give coordinate system, well, otherwise you don't have coordinates. So I still have the same momentum, rho v, and that momentum has two coordinate values, rho vx and rho vy, correct? And both of them have to transfer across this y plane. So if I put and imagine if this indeed was some sort of object, I can imagine that I'm sitting in a fluid. Okay? object sitting in fluid. How stressed would it be, right? From that fluid moving around it. So this side of the object will feel the momentum. So inside the object, I don't have velocity, I don't have fluid, so I don't have velocity. So I'm feeling stressed from the fluid outside of it. And what's going to transfer is some x momentum across x plane. That's going to give me sort of normal stresses and some shear from different y velocities, right? They're going to transfer on that side. Okay. So basically, I'm going to have tau. What is going to transfer if I'm transferring x momentum? I'm going to call that shear stress. That's stress. No, it's not shear, actually. X momentum across x plane. XX. So tau XX. Okay. And the lower plane, same thing, right? It's just going to act in a different direction. And then my shear stresses, okay, are going to be parallel to this x plane, right? So they're going to be tau xy this time. Right? Now let's figure out how is this arrow going to point out. So xy, they're going to be parallel to these sides. So it's going to point this way or that way. This way or that way. All I know is that the opposite sides, they should point in opposite directions from each other. So how do we think about this? There's this object sitting in fluid. The fluid on this side, does it have a lower x coordinates or a larger? Huh? Lower. So this is where I'm going to make that stress point in a positive y direction when my fluid is in the lower x coordinates. And again, it's a convention. So that is my tau xy. And here it's acting in the opposite direction because my fluids are in. My fluid is in sort of larger If this is confusing, that's common. You kind of have to flip yourself and think who is in positive, who is in negative, who is in larger, who is in lower. Right? But these are all of the stresses that this box feels. Now, if I had in 3D, okay, I would have 3 stresses on each side. Right? So 2 shear, this and that, and 1 normal. They are all viscous stresses. I'm talking about viscous stresses. Now, if you had in mechanics, same thing is actually happening. So, general situation of stress. Let's say that I'm in subsurface, I'm 1 kilometer down. For one thing that is stressing me out is 1 kilometer of rock on top, right? That's for sure. So that's one vertical stress. But then the stresses that I don't think about it immediately, there are some horizontal stresses acting out. And they're really coming from like plates on top of the earth pulling and grinding against each other. So that's what's pushing and pulling. So at every point I describe the state of stress with 3 principal stresses, 2 horizontal and 1 normal. And if I'm in the coordinate system where those are maximized, like as extreme as they could be, this vertical and horizontal stresses. Then in that case, my shear stresses disappear, and my matrix describing the stress is actually really a diagonal matrix. In fluid, we will rarely have those shear stresses disappear because fluid kind of moves a lot. And we set one coordinate system that is sort of applies to everywhere, wherever it is that fluid moves. It's kind of rare that I have shear stresses disappear. I always stress and shear, right? And we have this full matrix also describing my stress state. And here I'm explaining what are the viscous stresses because of the dynamics of the fluid. Okay? Excellent. So basically, this is in 2D. In 2D, I would have my tau, the general matrix, be tau xx, tau xy, tau yx, and tau yy. So basically, this is my transfer across x plane, and this is my transfer across y plane, right? Viscous stress tensor. And now in 3D, what am I going to have in 3D? Tau xx, tau xy, tau xz. What's going to be the second row? Yx, yy, yz. Yes? So this is where my vector tau y is, right? That describes how x, y, z momentum components transfer across y plane. And this is where my tau x is, this entire row, right? And then my tau z, this is the vector that describes how rho vx, rho vy, rho vz transfer across a z plane. If z is pointing up, there's my z plane. Orthogonal to it, this is z plane. If this is z. Yes? Tau z z. Sometimes we use this to just denote tensor. Okay, so if you see this, it's, oops, what color? This denotes tensor. And sometimes it's just dropped for speed of writing. If you constantly and repeatedly write something, then constantly drawing those two might be too much. You can also see that in my speed of writing, this is how I write vector. So instead of a little full arrow, I put this half arrow on top. So these, again, are my normal stresses. Normal, viscous stresses. And the rest are shear. Good news is in terms of values, tau xy and tau yx are the same. So when you're actually calculating and you're evaluating things, even if you flip in your formula, what is x, what is y, you're going to be okay. You're going to arrive at the same number. So what we say is that n tau xz is tau zx, tau yz is tau zy. So good news is values, and I'm saying for values because the actual stress has a direction, right? And it's acting in different direction for tau xy. When I'm thinking about shear stress, it does have that force that is acting does have a direction. But when I look at the value in this matrix, right, that value is the same and tau xz is tau yz, x, and tau yz is tau zy. So we say that this matrix is symmetric, or stress is symmetric, described by a symmetric stress tensor. Tensor is an object, is something much more than just a matrix, but we think about it in 3D as a matrix. Now, conceptually, why we actually want to put things into a tensor is that action of a tensor, and why we want to actually describe things in this with this matrix, is that action of this tensor on any direction. Say that I'm not going to always be placing coordinate planes in my fluid. Say I put in a plane, right? What are the stresses on that plane? Relative to that plane, what's now important is what these stresses evaluate on that plane. And yes, I will have a normal stress to that plane, wherever my coordinate system might be. And I'm going to have shear stresses in that plane, wherever it is in my general coordinate system. So coordinate system suddenly that is relevant is that one that is oriented to the plane. In solid mechanics, you're going to have the same thing. It's just you're going to have a material fractures, and it fractures along some plane. That plane is now where it is, and whether you're going to have a fault and that fracture move along the fault, which is important in all kinds of things. Okay, if I'm injecting fluids, I might move faults. When faults move, what happens in subsurface? Maybe small one. Whenever we inject, it's not so big. Mother Earth can do bigger. But when we inject fluids, that basically messes up the force balance in this plane, and it might start moving. Okay? So in order to evaluate that, I have to know what are the stresses normal to that plane and shear to that plane. As the shear ones, if they overcome what's keeping it together, if they overcome the normal stresses times a friction factor, I'm moving. Okay? So, to evaluate that, I really just get the normal direction on that plane, and I multiply my tensor with a vector. And I'll get 3 stresses on that plane. Formally math. Okay? So that's why we like putting them in tensors. Also, it shortens writing. If I'm constantly writing down equations that are vector equations, these tensors shorten writing. They are, once you start writing, just numbers, then going back and forth is what's a little difficult. And, actually imagining and writing down this entire tensor back and forth. However, it does shorten writing, and there's a big value. Yeah? Okay. So let's see. I'm going to go back to my presentation. So when we actually think about, so these were dynamic stresses. Okay. And for fluid at rest, I also have static pressure that is there regardless, whether I have moving fluids or not, whether I have gradients in my velocity field or not. And that pressure is acting on all sides. Okay? So in this case, if I'm just thinking about hydrostatic stresses, okay, on each of those planes, I really have only normal stress. Yes? On each of the planes, I only have the normal ones. And I don't have shear for hydrostatic case. Okay? There's no pressure shearing. So if I'm thinking about that, describing this with a stress, I'm going to call it a hydrostatic stress, hydrostatic stress tensor. How would I describe it as a matrix? Do I have shear stresses in this tensor? No. So that's why I'm going to, in shear components will be 0. What are my normal components? P. Do they differ whether I'm X, Y, Z? Doesn't matter. For hydrostatic pressure, doesn't matter in which direction. So all of the others are P. Ain't that a beautiful, simple tensor? And that's why we actually think about pressure as a scalar, because one number describes it. Right? So one number, scalar P, is enough to describe hydrostatic stresses. However, if I want to combine it with my shear stresses, then I add it to the ones that we had before. And then this is my combined stress. This is all of the stresses I'm fed. No. Getting there. Yes? So this is basically combined hydrostatic and viscous stresses. And again, this happens when fluid is not moving too, so that's what I mean by static. And this happens because of the fluid movement. You will often have, this is the shortened notation. I'm thinking about tensors. This is identity matrix, so P times identity matrix. This is the shear stress tensor that I described before, and this is denoted as P. And also, if I'm thinking about direction stuff, so the way we describe it is Tij. Those are my components of tensor. There's this, it's called Kronecker delta Ij. It's 0 if I is different from J, zeros. And it's 1 if I is equal to J. So X component is 1, Y component is 1, and ZZ component is 1. So that just shortens notation. It's called Kronecker delta. So basically, when I think about one of these items here, the total, we think about it as total molecular force that's there both from fluid being static and fluid moving per unit area. And as we said, so basically, when we have the force, let's look at the tau yx. Okay. That was force in x direction felt on y plane. Okay. So this is the notation is in j direction, whatever j is, it could be x, y, z. In I direction. Force is in I direction. And area is perpendicular to, yeah. Woo!
You survived this. I can feel the stress in the room. Think about this. It is quite a lot, but it's the notation that took 100+ years in math to formulate. So I'm asking you to absorb it in one lecture right now. So give yourself some break to absorb it. Right? But it does shorten notation. Right? And then next time we will add more of the stresses that fluid feels. Now, our last question asks for evaluation in the homework of rho VV, which I didn't get to today. So let's do this. The last problem in homework, the one that asks for evaluating shear stress tensor, ignore it. We'll just defer it to the next homework. Okay? So work on first 4, because I didn't get to rho VV. Yes? So for homework, work for first 4. And the last one, we're just going to push to the next homework. Yes? Because for that one, you know only half of the definitions you need. Okay? Yeah? All right. Well, enjoy the weekend. I hope you're not too stressed out. I will also, ahead of next class, I will send a couple of videos about basically reviewing calculus, gradient, and divergence, because we'll need it. Okay? And I will upload this new lecture. You too? You too? Enjoy the weekend. See that?